Look up on a clear night, and the sky feels peaceful. Yet beyond that silence, you're staring into a chaotic arena of spinning planets, galaxies racing away from each other, and forces powerful enough to crush stars. It forces us to ask, can a human mind actually comprehend something this massive and complex? In his book, A Brief History of Time, physicist Stephen Hawking took on that exact challenge. To understand his approach, you have to look at science not as a fixed list of absolute facts, but as a map-making process. A scientific theory is just a model. We observe patterns in the universe, draw an explanation, and test it to predict future events. If a prediction works, the map gets stronger. But if even a single new piece of evidence disagrees with it, the entire map has to be redrawn. One of the first great maps of reality came from Isaac Newton in the 1600s. He described a universe governed by laws, where objects naturally keep moving unless a force stops them, and where gravity pulls masses together. His equations proved that the exact same rules causing an apple to fall to the ground on Earth were dictating the orbital paths of massive planets moving around the Sun. That model worked for centuries, until scientists measured the speed of light. They discovered that light travels at a constant speed of about 186,000 miles per second, regardless of how fast you are moving toward or away from it. If the speed of light never changes for anyone, then something else has to adjust to make the math work. Our standard measurements of space and time have to bend. To fix this glitch in our cosmic map, Albert Einstein developed the theory of relativity. Einstein showed that space and time are woven together into a single flexible fabric. Place a massive object like a star in the middle of this fabric, and it sinks, warping the grid. Send another object nearby, like a rolling marble, and it follows the curve instead of moving straight. Matter tells the fabric of space-time exactly how to curve, and in return, that curved space-time tells the matter how it needs to move. That curvature is what we experience as gravity. But Einstein's smooth, curving map only works on massive objects like planets and stars. When you zoom in to the microscopic scale of electrons and photons, those rules fall apart. Down here, we enter the world of quantum physics. Scientists discovered that you can never know both the exact position and the exact speed of a particle at the same time. The closer you look at a particle's location, the more uncertain its speed becomes. Because of this uncertainty, tiny particles do not move like solid billiard balls. Instead, they act like overlapping waves of possibility, existing simultaneously in a wide range of possible locations all at once. Massive things we can see and touch feel solid, but the invisible building blocks underneath them operate entirely on chance. To see where our current maps reach their breaking point, we have to look at the most extreme environments in the universe, black holes. These are the natural laboratories where the massive gravity of relativity meets the microscopic world of quantum physics. When a giant star collapses under its own weight, it shrinks down to an infinitely dense point called a singularity. The gravity is so intense that beyond the event horizon, escape becomes impossible, even for light. At least, that was the initial assumption. Stephen Hawking realized that quantum activity near the event horizon changes the rules entirely. Tiny particle pairs appear right at the edge. One escapes while the other falls in. The black hole is actually emitting a faint heat. Because it is constantly leaking this radiation, the black hole loses mass. Over unimaginable spans of time, it will slowly shrink and evaporate away entirely. Hawking's discovery that black holes radiate heat connects them to the universal second law of thermodynamics. It means black holes possess entropy, the tendency for disorder to increase over time. It's why a cup can fall and shatter into 100 pieces, but those scattered pieces will never spontaneously jump back up and reassemble. Our experience of time is tied to this process. We remember the unbroken cup in the past and observe the scattered pieces in the future. Time moves forward for us because the universe's disorder is always increasing. If you trace that timeline backward, past the black holes and the stars, the universe contracts. It gets hotter and denser. until you reach the Big Bang, a moment where all matter and energy were compressed into something both infinitely heavy and microscopically small. This illustrates the problem in modern physics. If you try to use the smooth curves of relativity and the chaotic waves of quantum mechanics together to explain the Big Bang, the equations mathematically crash, producing impossible infinite numbers. This mathematical breakdown tells us our map is incomplete. To truly understand the origin of the cosmos, we need a single unified map, a theory of everything. We can measure the forces shaping reality today: gravity, electromagnetism, and the two nuclear forces holding atoms together. But finding the mathematical link that ties all four forces back to one shared origin point remains an open mystery. Hitting the limits of our current equations is not a failure. It reveals exactly where the next answers lie, waiting for anyone curious enough to look up at the night sky and try to draw a better map.